Well, good morning. We are going to back up and go to inverse functions in Chapter 5. I think right now, with the distance learning, this might be a more beneficial option for you. It's something that you will need in the future, and it's something that you have seen before, so it's not a totally new or totally different concept. So we're going to begin Chapter 5 today talking about inverse functions. And I have a relation written down here. That relation is H. And one of the ways that we can name a relation is with a set of ordered pairs. We can show it on a graph. We can have a relation that's designated by a particular function or by a particular equation. So what we want to do is look at this relation. In this relation, the first values are called inputs. In other words, the -6, the 0, the 3, the 5, and the 2.7 are inputs, and these inputs comprise the domain. And the second number, I can't spell, domain. The second number is the output, and all of the outputs comprise the range. If you were looking at the graph of, or a graph, the x values, remember, are the domain, the y values are the range. So in order to get the inverse relation, you probably remember we just switch the inputs and the outputs. So we switch the inputs and the outputs. So the inverse of H is going to be the set of ordered pairs 2, -6, 1, 0, 5, 3, and 3.7, 2.7. Notice when we found the inverse, the domain and range switch places. The domain and range switch places for the inverse. The domain and range switch places when we have an inverse relation. I want to graph the relation G, which is made up of the set of ordered pairs 0, -1, -1, 2, and -2, 5. I want to graph that relation, and then I want to graph its inverse. So let's first graph these points. I'm going to make this grid a little bit bigger, might make it a little bit easier to graph. So 0, -1, -1, 2, and -2, 5. So just graph those points. If I wanted to, I could connect them because I think this is linear. Looks like you've got a slope that's consistent. Now, if we want to graph the inverse of G is going to be the set of ordered pairs -1, 0, 2, -1, and 5, -2. Some of the work you'll be doing, you'll be graphing some functions and their inverses, and if you'll get ordered pairs from the first one, then you just switch those points, switch the x and the y, and you can graph the inverse. So we have the point -1, 0. Do it in a different color so you can see it. 2, -1, and 5, -2. And I'm going to connect those because I want you to see, I hope you can see, especially those of you that are artistic should be able to see that these two parts of a line reflect across the line y = x. Inverse relations and inverse functions, inverses reflect across the line y = x. They will always do that. Now, another way that we can define a relation is with an equation. And to get the inverse for the equation, we simply switch the x and the y. For instance, if we have the relation y equals x squared minus 5x, if I want the inverse, I switch the x and the y, and we get x equals y squared minus 5y. Some of you may remember doing this before. If we're working with functions, then we usually will solve for y. But notice in this equation, it'd be kind of hard for us to solve that one for y. So what I want to do is graph the original function and graph its inverse. And to do that, the simplest way is to do a t-chart, set of ordered pairs. If we do the function, then it's very, very easy to get the points for the inverse. So here we're going to have x and y, which equals x squared minus 5x. So I'm going to just choose some points. I'm going to let x equal 0. That's always an easy one, so y is 0. I'm going to let x equal 5, because I looked at this and I can see that if x is 5, we're going to have 25 minus 25, which is 0. So those two are pretty easy. If I let x equal 1, we're going to have 1 minus 5, which is negative 4. And we'll do one more. We'll let x equal 2. And if x is 2, we have 4 minus 10, which is negative 6. Now the points that I'm going to use for the inverse function are simply the reversal. So we're going to have 0, 0. We'll have 0, 5, negative 4, 1, and negative 6, 2. See how easy that is when you get the points for that original equation. So we're going to go ahead, since I'm in red, I'll go ahead and graph the inverse first. We have negative 6, 2, negative 4, 1, 0, 0, and 0, 5. If I graph these, it looks like this. We have a sideways parabola. Let's look and see what happens if we graph the original equation. We have 0, 0. That overlaps. I have 5, 0. 1, negative 4. And 2, negative 6. So here we have a parabola that opens up. And if we were to draw the line y equals x, hopefully we can see that there is a reflection across that line. You artistic people probably see that a lot better than I do. But those graphs reflect across the line y equals x. That is a characteristic of inverse relations and inverse functions. We need to remember that a relation is a function if it passes the vertical line test. In other words, if you were to draw a vertical line through the graph of an equation, and it only touches the equation once, it passes the vertical line test. Okay, so let's look at, if this were our function, I could draw a vertical line anywhere through this graph, and it would only touch the graph one time. If I had a parabola, and I draw a vertical line anywhere through, it only passes through once, so that is a function. If I have this graph, sideways parabola, and I draw a vertical line through, it does not pass the vertical line test. So this is not a function. And we say, in order to have a function that for each element of the domain has exactly one element in the range. Each element of the domain in other words, the x values has exactly one element in the range. That's definition of a function. And we can see in the one that did not pass the vertical line test that for 0, when the domain was 0, there were two values for y, two values of the range. So that's the reason that that is not a function. Now, just because we have a function, that does not mean that the inverse is necessarily a function. If a horizontal line passes through the function only once, then its inverse is a function. If it passes the horizontal line test. Okay, the horizontal line test. I'm having some technical difficulties here. If it passes the horizontal line test, in other words, we draw a horizontal line through the function, it passes if a horizontal line, and I'm going to abbreviate, a horizontal line intersects the graph only once, then the inverse is a function. Okay, it passes if a horizontal line intersects the graph once. That means that the inverse is a function. And we say that the function is 1-to-1. The original function is 1-to-1. So if a function is 1-to-1, that means that it has an inverse that is also a function. If the function is 1-to-1, that means that it passes the horizontal line test. If a function is 1-to-1, the domain of the function is the range of the inverse. And I'm going to put some different terminology here for inverse. I think you've seen this before. It's the range of the inverse. That -1 does not mean 1 over f of x. It's for the inverse. The range of the function is the domain of the inverse. That's that's a more complicated way of saying that x and y switch places. A function is also 1-to-1. These are characteristics of a function. A function is 1-to-1 if it's either increasing over its domain or decreasing over the domain. You can hear my dogs. They're worse than a 2-year-old wanting attention. So, to restate all that, if a function passes the horizontal line test, a horizontal line only intersects the graph once, means that it is a 1-to-1 function. Its inverse is a function. The domain of the original function is the range of the inverse. The range of the function is the domain of the inverse. In other words, x and y change places. And it is, if it's 1-to-1, it is 1-to-1 if it's increasing over the domain or it's decreasing over the domain. Let's quickly look at some functions and see if we can determine if they're 1-to-1. I'm just going to go ahead and draw some quick grids. So I can switch colors. All right, if we have a linear function, that does pass the horizontal line test, and so this is considered one-to-one. In fact, it's increasing on its domain. Over the whole domain, it's increasing. And we could say anytime you have a linear function, it is always going to be one-to-one, and its inverse will always be a function. If I had f of x equals x squared, hopefully you remember from earlier in the year, this is just a parabola whose vertex is at the origin. F of x equals x squared. This does not pass the horizontal line test, so this is not one-to-one. Because if I draw a horizontal line through that parabola, it's going to intersect twice. If we have, let's say, the function, I hope you'll just take my word for it, it looks similar to this. The cube root of x plus 2 plus 3 looks something like this. And notice that that is increasing over the domain. It doesn't go up and then come back down. It doesn't go down and then come back up. This is one-to-one. If it goes up and comes back down, then it is not a one-to-one function. If you have a function that looks something like this, notice it goes up, it comes back down, it goes back up, it comes back down. If we were to draw a horizontal line through this function, it's going to intersect more than once, so this one is not one-to-one. All right, now let's look at some examples or look at how we would find the formula for the inverse function for a one-to-one function. How do you find that inverse function? Well, first of all, replace f of x with y. F of x simply means y. In calculus, we normally will use f of x, but f of x means y. So we replace f of x with y. You switch x and y. You solve for y. You probably remember doing this before. Solve for y. And we replace y with the inverse notation, which has a little -1 there. Remember, that it's not an exponent. That means the inverse function. Remember when we were trying to, we were in trigonometry on your calculators where sometimes you had to find the angle. You had to use the inverse function key. I decided that we would skip the part of working with inverse trig functions for right now. So let's just look at a simple linear function. F of x equals 3x plus 7. And let's see how we go about finding the inverse. Step 1, replace f of x with y. It's always the first step. Then switch x and y. Let me erase that. Okay, so we're going to have x equals 3y plus 7. And I'll come over here. X minus 7 equals 3y. And divide both sides by y, and we have x minus 7 over 3. Or we're really not finished until we say the inverse function of x equals x minus 7 over 3. And that is the inverse of the original function that we were given. Okay, now let's see if we could check that to make sure that we have it, that's an inverse. One way we can do that is by finding a point on the original function and seeing if that point reversed fits in the second function. Okay, so in other words, let's let x equal 1 over here for our original function. So if x is 1, in other words, if we find f of 1, that's going to be 3 plus 7, which is 10. So what I want to do is see, that's the ordered pair, 1, 10. Let's see if the point 10, 1 is in the inverse, if that makes that a true statement. So if I find the inverse at 10, I should get 1 if I did it correctly. So we would have 10 minus 7 over 3, which is 3 over 3, which is 1. So yes, those two functions are inverses of each other. In a few minutes, we're going to look at another way to prove that functions are inverses, but that's a quick way to do it with this simple function. Okay, let's look at another function. G of x equals x cubed plus 2. All right. This is a one-to-one function. Hopefully you know what this looks like. It is a cubic function. We know the end behavior from last semester should look like this. And it's only going to turn once. Actually, that graph is going to cross at 2. And it's going to look something like this, increasing on its domain. So that is a one-to-one function. You can always check it on your calculator, your graph, to see if it's one-to-one. And remember, it's 1-to-1 if it passes the horizontal line test. So to find the inverse, we switch x, or first of all, we plug in a y for g of x. Switch x and y. And solve for y. X minus 2 equals y cubed. And then to solve for y, we take the cube root of both sides. X minus 2 equals y, and we're not finished until we write it in inverse function form. Cube root, the inverse, sorry, that wasn't f, that was g. The inverse of g of x is the cube root of x minus 2. Now, if we want to choose a test point, we could solve for g of 0. And if we solve for g of 0, in other words, the x value is 0, the y value is going to be 2. We have the point 0, 2. So let's see if the inverse, if we plug in a 2, if we get 0. The cube root of 2 minus 2, which is 0. The 0.20 is on the inverse, so we did that correctly. Okay, I want to graph these two functions. Those are not necessarily things that are just real easy for us to look at. Let's do a t-chart. That's always a good option if you don't know what the graph of something looks like. So we have x and y. We know we have the 0.02. We've already found that one. If we let x equal -1, then we know that we have -1 plus 2 is 1. If we let x equal -2, we have -8 plus 2 is -6. And if we let x equal 1, we have 3. So that's enough points for us to see what that looks like. We have the 0.02. We have the point -1, 1. And we have the point -2, -6. And the 0.13. And the graph looks like this. A little similar to what I had before. It extends, it keeps on going. Now let's look at the inverse points. Let me do that in a different color. We already know we have the 0.20, 1, -1, -6, -2, and 3, 1. Not hard to graph the inverse once you have points for the original function. So we have the 0.20, we have the 0.1, -1. Kind of hard to get it on this small grid. 3, 1. And -6, -2. So we can kind of see this is going to look like this. And if I were to graph the line y equals x, this one is a little easier to see that it reflects across the line y equals x. Okay, I want to work one more that's a little bit more complicated, and you've got one like this in your homework. So I want to be sure and work this one for you so you can see how to do it. It's just the algebra. F of x equals 5x minus 3 over 2x plus 1. You can always look at your calculator. You can look at this graph and see that it is 1-to-1 because it does pass the horizontal line test. Remember, first step, change the x and the y. Hopefully you're taking notes, or you'll keep this easily bookmarked so that you can go back and look at it if you need to. It'd be better to take notes. Now what we want to do is solve for y. And excuse me, I did not do that. Let me erase this. Change that to an x. Looks kind of tricky to try to solve this from y. So what I'm going to do first is multiply both sides by 2y plus 1 because I don't want to have that complex fraction. So we're going to have x times 2 equals 5y minus 3. Distribute that x. And then group the y's together on one side and everything else together on the other side, just like you've done since Algebra 1. I'm going to add 3 to both sides and then subtract 2xy. So we'll have x plus 3 equals 5y minus 2x. Hopefully you can see what I did there. I added this 3 to both and I subtracted 2xy from both sides. Now on the left side I can factor out a y, and we have y times 5 minus 2x. And if we divide both sides by 5 minus 2x, we get y equals x plus 3 over 5 minus 2x. And we're not finished until we put it in function notation. The inverse of the function is x plus 3 over 5 minus 2x. It would not be wrong if you had 3 plus x on the top. Would not be wrong if you had negative 2x plus 5 on the bottom. Now we're going to take just a couple more minutes and talk about the composition of a function with its inverse. The composition of a function with its inverse. The way that we show it mathematically, and I think you've done this, maybe you've done this before, there's 2 ways to show it. F and then a little 0. I'm not sure why textbooks show it that way. To me, that's a little bit confusing. Calculus tends to do that. Another way that we could write it is f of the inverse of x equals, it will always equal x if they are inverses of each other. And if we go the other direction, the inverse of f of x, or I like this way of writing it better. It kind of helps me to see what I need to do. That's equal to x. That's how you can show that two functions are inverses of each other. For instance, let's say that we have f of x equals x cubed plus 2, and its inverse, supposedly, is cube root of x minus 2. And I want to show that these two functions are inverses of each other. All right, so I'm going to do f of the inverse. What this means is that in the function, wherever I have an x, I plug in the inverse. So I'm going to plug the inverse function in for x. We're going to have the cube root of x minus 2 cubed plus 2. Now notice, when we cube a cubed root, we just get x minus 2 plus 2, which equals x. So that checked. Let's see if it checks going back the other way. If we take the composition of the inverse with the function. Okay, this time, using the inverse function, wherever I have an x, I'm going to plug in the original function. So we have the cube root of x cubed plus 2 minus 2, which is the cubed root of x cubed, which equals x. First assignment for this quarter, and it is going to be on page 319. It's 3 through 15, every third, times 3 means every third. 25 through 32, those you're just looking and saying yes or no. Write the equation. You don't have to write the graph, but write the equation and say yes, it's 1 to 1 or no, it's not. 33 and 36. 45 to 54, every third. I know it sounds like a lot, but most of these are very simple to do. 67, 70, and 74. Haven't decided exactly how we are going to keep up with all the homework. I would highly encourage you to do it. It's quite likely that I may give homework quizzes where you just have to find one of the problems and give me the problem worked out correctly with the answer. But for starting out, we will check these on Wednesday. And I really don't think you'll have any problems with them. If you have a question, go back and look at your notes, or you can go back and pull this video up and look at parts of it again. Thank you.